Hello guys! In this video we are going to see another example of function, real function, that is the circular speed of an object orbiting a main body. Okay, which are the objectives of this video? Okay, the objectives is going to study different types of orbit and their applications, starting with circular orbits. And we also going to apply mathematical functions to calculate this orbital speed when an object is moving around the Earth. Okay, requirements are very low. I mean, with a little bit the knowledge on calculus and calculating derivatives, it's more than enough. And also, we will need a little ability to interpret mathematical models. But okay, I will try to explain everything we need during this video. We are going to start with a function that is called the circular speed. Consider the following situation. We have the Earth, could be any other object. Okay, let's start with the Earth. We have the Earth and something orbiting the Earth. Could be satellite, the International Space Station, or anything. Or an asteroid if you want. Okay, the idea is that we want to find a function that, provided the distance from the center of the Earth, this function gives us the circular speed of the object. We are going to consider that any object is orbiting in a circular orbit, okay? We are not going to consider now ellipses, okay? Only circular orbits. Okay, so the function is piece of cake. The function is very simple. It's just the square root of the standard gravitational parameter of the main body we are orbiting divided by the distance of the object that orbits the main body. Be careful because the distance is from the center, okay? There is a confusing idea when we talk about the altitude of a satellite. Well, that means that when we say altitude, we are considering the distance from the surface of the Earth till the object, okay? So, let's see. The gravitational parameter of the Earth, that is the one we are going to use in the examples, is going to be given in kilometers cubed divided by seconds squared. And the distances are going to be calculated in kilometers. Probably you are thinking, okay, this is not the best units you can use. I know, okay, but since we are not going to be very far from the Earth, let me use these kilometers. At the end, as you just calculate the function, then the speed is going to be given in kilometers per second. Okay? So, let's see an example. It's a very easy function. I'm just focusing on the mathematical idea. We have a function that gives you the circular speed of an object orbiting the Earth. Okay, which object are we going to take first? The International Space Station. It's an object that is orbiting in a LEO orbit, low Earth orbit. It's very close to the Earth, around 400 kilometers from the surface of the Earth. Be careful. What is the distance of the International Space Station from the center of the Earth? You need to add the radius of the Earth. So the distance in this case is 6,771 kilometers. Which is the speed? Okay, let's use the formula. Piece of cake, guys. It's nothing difficult in here. So it's the square root of mu divided by 6,771 kilometers. And this gives you, at the end, if you calculate it using any calculator, 7.6667 kilometers per second. It's very fast. It's very fast. Remember that it's kilometers per second, not per hour. Okay, it's really, really fast. Recall that the International Space Station complete a full orbit around the Earth in 93 seconds. Okay, 1 hour and a half. Okay, so it's orbiting very fast. Remember this value, okay? Now, let's take another object, now in a completely different altitude. We take low Earth orbit to begin with, and now we are moving very far from the Earth. We are moving to 42,164 kilometers from the center of the Earth. This is not an altitude in this case, considering Earth radius, okay, it's included. Okay, so applying this circular speed formula, we just replace the value for mu, gravitational parameter of the Earth, divided by this radius, you obtain 3.07 kilometers per second. Okay, Probably you remember perfectly the previous result. ISS has 7 kilometers per second, and now we have 3. What is happening? Is it true that when we move away from the Earth, the circular speed decreases? Okay, let's see from a mathematical point of view. Here, in the next slide, what you have is the circular speed of an object in terms of the radius or the distance from the center of the Earth. Okay, I just here rewrite the function in a different way. I'm just trying to make it easier to calculate the derivative. Is it necessary? Probably you are asking yourself. No. I'm completely sure you can just calculate the derivative really fast by your own means that probably are better than the ones you see on the slide. But since I'm not really sure how you deal with derivatives, I prefer just to write it in a easier way, or in my opinion, probably some of you could think that I'm complicating things. Okay, anyway, the idea is that you have a square root of a quotient. This is the square root of the numerator and denominator. And in the denominator, I just wrote the square root as a power function. I mean, this is r power 1/2. It's exactly the same as the square root of r. Then I don't like to have r on the denominator, so I just move up r just by changing the sign of the exponent. Now, this is easier to calculate the derivative because square root of mu is a constant that remains the same when we calculate the derivative, and the derivative of a power function like this is solved as follows. I mean, the exponent goes down, as you can see, and then we subtract -1 to the exponent we had before. So -1/2 minus 1 minus 3/2. Now, the rest is just to, this is the derivative, it's already calculated, but I'm going to rewrite the derivative as a quotient. So, as you can see, the exponent is negative, so I can write down r, but power to positive 3/2. What is r power 3/2? Is the square root of r cubed. We have a square root on the numerator, a square root on the denominator. We can just put it or write it together, as you can see on the blackboard. Okay, so what this function give us as information? Okay, as you can see, I have a negative sign. Second, the radius or the distance from the center of the Earth is going to be positive. Could it be 0? No. Be careful. Look at the function. We are dividing by r, and does it make sense to rotate or the distance to be 0? Are you in the center of the Earth? Which is your speed? Okay, so it doesn't make sense. So the domain is going to be from 0 till plus infinity. Be careful. You can just tell me. Probably you are thinking, no, you are wrong. If we are talking about satellites orbiting the Earth, it doesn't make sense to start at 0. At least should be the radius of the Earth. I know, guys, you're right. Okay, I just took 0 positive infinity because I was thinking as a mathematical function, okay, that it doesn't mean anything, or it has no meaning just about the mathematical expression. But you are right. The domain, if in real life, should be at least the surface of the Earth. And if you are thinking, okay, but be careful because you have an atmosphere, a very dense atmosphere, very close to the Earth, so probably it's making even better to consider the domain about 200 kilometers of altitude from the surface of the Earth till infinity. That makes sense, okay? But allow me to just use 0 plus infinity because it's just more close to the mathematical idea I'm looking for, okay? So, important thing, at least, is that the radius is going to be positive. If you replace any positive radius in this formula of the derivative, the square root is going to be positive. The cube is positive, and the mu divided by a positive number is positive, the square root is positive. Oh, wait, we have a negative value here, so it's going to be negative at the end. So for any value in the domain, the derivative is negative. The derivative is negative means that the function is decreasing as expected. As we have seen in the previous examples, we started with a low Earth orbit, really fast, orbiting really fast. Geosynchronous orbit, really slow around the Earth, sorry, like this. And so it's a decreasing function. We had proved before. We have seen examples before. Now we know it for sure. If you want to plot it, look at this graph. the farther we go from the surface of the Earth, the lower is going to be the speed. Remember that this is in kilometers per second, and geosynchronous are more or less around here, 3.0, whatever we obtained before. Okay, exercise. You can calculate the circular speed of Mars if you just change the gravitational parameter, because Mars is not orbiting around the Earth, it's orbiting around the Sun. So you need the gravitational parameter of the Sun. Remember that there is a mistake here, it's 10 power 11. And the semi-major axis is going to play the role of the radius because it's very close. The idea is the eccentricity of Mars is very small. So it's exactly like more or less like a circular orbit. So you can calculate this speed. Even better if you build a code in Python to calculate the speed of the planets. Even better if your code allows you to select which is the main body we are orbiting around. And then you can just choose if it is the Earth, if it is the Sun, if it's we are calculating the circular speed of the moons of Jupiter. I don't know. Okay, but you only need to take care of the gravitational parameter you are going to use, okay? In this case, the exercise is very simple. You only need to divide this number by this number and obtain the square root. And what you are going to obtain is that the speed of Mars is 24 kilometers per second, around 24 kilometers per second. Okay, just one remark at the end and we finish this video. This is a very simple function. It's a very simple function. It's only giving you the speed of an object orbiting another one. This function gave the first ideas of the dark matter. It's this for sure. We haven't proved anything with this formula. The idea is that if you expect something to be rotating at some speed, and you discover that it's faster, probably the mass in between is bigger. Okay, so if you are talking about the circular speed around galaxies, okay, and you discover that the speed is faster, and you calculate the mass in between, okay, something is wrong. It's going faster than it should be, and this is because maybe there's some mass in between that we are not seeing. So this function gave an idea that something was happening, something not exactly like the way should behave the things. So that was the first indications that something was not right. So this, for sure, this has been proven in many different ways, and it has been explained in a much more specific ways. But this function gave an idea of something was happening and may put the focus on what is happening. Maybe some mass is still there and we don't see it. Okay, so what have we seen in this video? The basic principles of orbital mechanics, and we have seen some orbits, circular orbits in this case, and calculations for ISS and geosynchronous orbits. Thank you for your attention and see you in the next video.